With point-to-point-bridge, we approach the task of point cloud denoising using diffusion models. While most previous work is based on the assumption of Gaussian noise, our method is trained as a data-to-data diffusion bridge, meaning that it can be trained on any paired noisy and clean data. This allows our method to learn intricate noise patterns and characteristics, leading to an improvement over existing works on denoising single objects and scene reconstructions. With the improvement in scanner technology such as LiDAR, cheap scanning devices are increasingly incorporated in off-the-shelf products, allowing users without professional equipment to gather 3D scans of objects. These scans are often represented as point clouds, as this is a simple and intuitive representation of 3D data. However, these scans are often corrupted with noise due to factors such as low scanner resolution, distortion, limited range, or environmental factors such as occlusion or difficult lighting conditions. Denoising point clouds can enhance applications in virtual and augmented reality, 3D modeling, or autonomous driving. However, most of the previous methods rely on the assumption that the noise follows a Gaussian distribution, which may not be enough to capture the noise characteristics found in real-world scans. We can summarize our key contributions as follows. We present a novel approach, P2P-Bridge, for denoising point clouds. Our method is inspired by the Schrödinger bridge problem and formulates point cloud denoising as a tractable data-to-data transformation process. Furthermore, we propose integrating high-level features like Dino v2 to guide the denoising process for semantically informed denoising. Let's take a look at how a data-to-data diffusion approach works in the context of point cloud denoising. Our diffusion-based approach involves taking a noisy point cloud and determining the overall level of noise present. This allows us to subtract the estimated noise from the original point cloud, resulting in a less noisy point cloud. We can repeat this process until the estimated noise reaches zero and the point cloud is fully denoised. Our method is highly effective, producing impressive results with as few as 5 to 10 denoising steps. To achieve this, our model is trained on generating a so-called diffusion bridge. Diffusion bridges, in particular Diffusion Schrödinger bridges, are a type of diffusion model that can transform any prior distribution into clean data without relying on Gaussian priors. Our methods adapt to previous works on diffusion Schrödinger bridges to point clouds specifically. It is designed to determine the optimal transport plan between noisy and clean data distributions. This means that our method is trained on transforming a noisy prior distribution of points into a clean distribution while applying minimal displacements to the points. Let's dive into the full pipeline of denoising real-world point clouds obtained from indoor scene reconstructions. Our experiments on real-world data involve using noisy reconstructions from ScanNet++ and ARKit scenes. The professional laser scan point clouds act as ground truth data. In the first step, we pre-process the data. When scanning real-world objects using mobile devices, there are usually additional RGB frames available. To improve the accuracy of the model, we suggest utilizing both the RGB information and semantic features extracted from Dino v2 as additional pointwise features. By projecting these features onto a point cloud of the scene using the camera poses and intrinsics, we can enhance the model's performance. In the second step, we can train the diffusion bridge using paired noisy and clean data. This is accomplished using so-called noise prediction, which was introduced in denoising diffusion probabilistic models. By sampling a latent point cloud XT, which is an interpolation between the noisy and clean data. Our model predicts the noise added to the clean data, resulting in the noisy latent sample XT. In the final step, we apply our model directly to noisy data and denoise it in an iterative manner. Let's see how this approach compares to previous works on point cloud denoising. First, we evaluate the effectiveness of our approach by comparing it with previously proposed deep learning-based methods on the PCNet test set. To simulate noisy input, we artificially add Gaussian noise to the ground truth data. The variance of this noise corresponds to 3% of the object bounding box diagonal. Our approach outperforms existing works by generating smoother surfaces and sharper details. According to the evaluation on ScanNet++, there is a noticeable difference between noise-to-data approaches, such as score-denoise, and data-to-data-based approaches, such as PDFlow and our method. Methods based on the assumption of Gaussian noise fail to recover fine details. Additionally, score-denoise produces artifacts due to patch-based processing. This is because the model cannot differentiate between the border of real objects and borders due to patch-wise processing. as it assumes Gaussian noise in the data. Although PD flow does not suffer from such artifacts, it lacks the ability to restore sharp edges. Our approach can generate both smooth surfaces and recover fine details. We additionally conduct experiments on ARKit scenes. Due to the lower amount of detail in the noisy scans of ARKit scenes compared to ScanNet++, the denoising is generally less pronounced. Nonetheless, our method produces sharper edges of objects and smoother surfaces compared to the other methods. There are also incomplete objects visible, which none of the methods can complete. To tackle this, future works could incorporate strategies from point cloud completion. In conclusion, we presented P2P-Bridge, a point cloud denoising framework based on diffusion Schrödinger bridges. It approaches the denoising task as a data-to-data diffusion problem by learning an optimal transport path between point sets. Furthermore, we advocate for semantically informed denoising by incorporating high-level features, such as Denoising, to guide the denoising process. We applied our method on single-object datasets, as well as large-scale indoor point clouds. Experiments showed that our method outperforms prior works on single objects, as well as large point cloud data.